So hello everyone, this is lecture 6 for the electricity and magnetism. In the last lecture we were discussing about the electrostatic potential. Today we'll see what is electrostatic energy. So the definition is it is total work done in assembling all charges. Means you have some system. So total work done is required to assemble that system is called the electrostatic energy. Now what is electrostatic energy for a particular charge? Means if you have this system and at a point due to these all charges the electric field is in this direction. Now you have a charge at this point, that is capital Q, and you need to move this charge from A to B. So that amount of work required to bring this charge from A to B is called the electrostatic energy for that charge. Okay, so let's see how can you find how much work is required. So W will be work done equal to F dot dl, and from A to B. So this is the general formula for work done. Now force in the reverse direction of electric field. So we'll use force is nothing but Q multiply electric field, and electric field is in this direction. So force direction will be in this direction. So it is minus E. So minus QE. Now dot dl. Now see, Q is constant, so we can take this out. It will be minus E dot dl A to B. So this is the formula for electrostatic potential. So we know E dot dl minus is given by VB minus VA. So this work done will be Q VB minus VA. And see, this is independent of path because it is depending on the initial and the final position of only. With the potential at the initial and the final position. So this work done will be independent of path, and that's why our the electric field is conservative in nature. Now if we assume that A point is at infinite and we are bringing that charge to the B point, that is at r distance from the, means at the r distance, r vector from the origin. So how can we find the work done? Then it will be we will assume that at infinite the potential is 0 and we need to find at the VB. So it will be, we assume B equal to R, so it is at R distance from the origin. So it will be W equal to Q VR minus V infinite, so equal to Q VR. So this will be your work done or the electrostatic energy for that charge Q at B point. So that is your potential. So what you will do, first you will calculate the potential due to all these charges at this B point, and then you will just multiply the charge with this potential at this point. Then it will give you your electrostatic energy for that charge, okay, at this point. So you can find this. So this will be equal to Q VR, and this is the potential at the B point due to all these charges. So let's see how can we define for the n charges the system. So for two charges, you have only two charges, so how much electrostatic energy for these two charges will be there to arrange this kind of system. So for this first charge you don't need any work done, so because there is no potential around, so there will be work done will be 0 to bring this charge. Now to bring this second charge, there will be potential at this point due to this charges, and the potential will be V1. So we'll need a work done, so that will be equal to V1 multiply Q2. So V1 is nothing but Q1 divided by 4 pi epsilon R12, and multiply Q2 will give you total work done. So W2 will be this, and W1 equal to 0. So total work done to arrange this system is W1 plus W2, that will be this. Now if there is Q3 charge also, now W1 will be 0 again. To bring second charge, the work done will be this. Now to bring this third charge, you need work done equal to Q3 multiply potential due to these two charges at this point. So potential at this point will be V1 plus V2. So V1 will be Q1 divided by 4 pi epsilon this distance, and V2 will be Q2 divided by 4 pi epsilon this distance. So let me denote it by 1 3 and 2 3. Okay, so this will be your potential, and means this V1 plus V2 will be this, and multiply Q3. This will be your work done to arrange this 3 charge, means to bring this 3 charge, this will be your work done. And for this Q2 this will be your work done, and for first charge this is your work done. Now for complete, you just add them. W1 plus W2 plus W3 will give you total electrostatic energy to make this complete system. So this will give you this. So this is your complete electrostatic energy to arrange this kind of system for 3 charges. Now if we have n charges, means n charges we have, so what will be the general formula for them? So you can see here that if we replace this 1 by I and this 2 by j, so this is I is always less than j, so we can arrange them by this way, means we will always take only those cases where this 1 is, means I is less than j. So 1 2 1 3 2 3. So 2 1 is also same, but we just put this condition that I should be less than j. Then we will get our complete thing, means if there are 3 particles, then all the combination are there, 1 2 1 3 2 3, all combination we have, and I is less than j. So we can write this in general form as this. For n charges, it will be W1 W2 W3 Wn. So 1 upon 4 pi epsilon naught Qi Qj Rij. So here we have all the combinations 1 2 1 3 1 4 1 5 1 6, then 2 3 2 4 2 5 2 6. All combination we will have, because the condition is I must be less than j, means only the condition is that I must be less than j, means you have 1 2 but you can't write 2 1. So that's how we will get this complete set. And we can use either condition, either I less than j or either I is greater than j, but there should be only one of them. So if I is greater than j, then you can write 2 1, 3 1, 4 1, but you can't write 2 1 as 1 2. Okay, so this is the condition. But if we say that we can write anything 1 2 2 1 2 2 3 2 3 2, then 1 2 can be written as 2 1. So there is two things same. We have the two same things, so we need to divide by 2 because we are getting something double. So that's why if we I is not equal to j and all possibilities are possible, means 1 2 is possible, 2 1 is also possible. So we need to divide by 2. That's how we can get our potential energy, electrostatic energy for the complete system. So I hope you understand this thing. Now let's take this qi outside and take this 1 by 4 pi epsilon naught inside with this. So we just separating them. So sigma I1 to n qi, we can write this in this way. Now see what is this. This is the potential at ith position, means at ith position you are finding the potential for all the jth particles, means for the q1, that is j is 1. So at it will be distance will be 1 1, means 2 1, means ri can be anything, means at this point if this is your ri. So to from the all the qj charges you are finding the potential at this qi charge. Okay, now this will give you potential for the particular means ith position, and you need to calculate for all the ith position. So VRI, we can write this complete as VRI, and this is nothing but potential at ith location due to all the jth charges. And now for the Q2, means I is changing, so for all the i's you have the potential, so you need to multiply this. So that's how you can find the total potential energy. So we can write this thing in this way also. So to make it easy, I can show you here also. As we are doing here, means we need to find the W3. Then we need to find the potential at this. This is just like this is ith position and these are jth charges. So we need to find the potential due to all jth charges at this ith location, and we just multiply q ith with the all the jth potential. This is the same case. We are multiplying the qi with all the potential at that position, means ith location, all the potential due to all jth charges. So this is the same condition, and we just divide by 1 by 2 because of this condition. So I hope this is clear to you now. Now this is for the discrete charges, means we have the different charges, means discrete charges system we have. Now if we have a continuous charge, then how can we find the electrostatic potential or the electrostatic energy? So for continuous charges, we need to replace this charge by the charge density. Okay, because we know this is the continuous charge density, or we have continuous charge distribution. That's why we need to take the surface charge density, volume charge density only, then we can say, because these are the things for the continuous charge distribution. So for the continuous charges, now this del q, means this qi total charge is written by rho d tau, and we need to take the integration. That rho is density, charge per unit volume, and this volume will give you total charge, and this v represent the potential at that position with which you are multiplying the charge. So now this will give you your total potential or the electrostatic energy. Now see this is charge density. So using the differential form of Gauss law, del dot E equal to rho by epsilon, you can write rho as epsilon del dot E v d tau. This v is potential and d tau is volume element, and you are taking the integral with in the whole volume. So now to find the value of this, we will use this identity. So divergence of del means del dot v, this is some scalar v and vector E. So this can be written in this way. The scalar will be outside, del dot E plus E del v. This can be written this way. Now see, this del v is nothing but minus E. We know this is the E can be written as some means gradient of v, some scalar. So this will be minus E, it will give you minus E square. So minus square E square will go this side and will be this plus E square. So this is this thing. Now this is equal to this plus E square. So in place of this, means we need this now, v del dot E we need. So in place of this we can write del dot v plus E square. So we just take this epsilon outside because this is constant, so epsilon by 2. Now E square integral, volume integral, and the epsilon by 2 del dot ve integral d tau. Now see, we will use the divergence theorem. So we can just convert this volume integral to the area element. So how can we do that? Means surface integral we can convert this. So this can be written in this way also, ve dot dA and the surface integral. So this is your total, means complete formula for the electrostatic energy for continuous charge distribution. Means here you are discussing our discrete charges, and you can simply find them by using these formulas for the discrete charges. But if you have some disk and on which, or you have dielectric sphere where the charge is uniformly distributed, then you need to use this formula to find the total electrostatic energy for that system. Now let's take an example. We have this dielectric sphere, means charge is uniformly distributed, and this is a continuous charge distribution. So this is not discrete charges, so that's why we need to use this formula. So here when you take the volume integral, so you need to take the volume integral from 0 to capital R, and for the surface integral you need to take for this complete surface. That's how you can find the total potential energy or the electrostatic energy for this system. Now see, we need to use this, and see, for any kind of system this must be constant, because this is the total energy required to assemble that system, so this must be constant. And see, we need to check, means we will use some trick here to make this equation simple, because here we need to find the volume integral, surface integral, and then we have to add. So this is a little bit complex. So how can we simplify this? So see, this volume element, if we increase the radius, means if we take the integral up to here, some increased value up to small r, then this term will increase, the value of this term will increase, and the complete should be constant, so this must decrease to make this constant. So this must decrease. As the r is increasing, this term will start decreasing to make this constant. So if we take r to the infinite, then we will assume that this will tends to 0. So we will get only this term, and that's how we can find the electrostatic energy for a continuous charge distribution by using this simple formula. And we need to integrate for in the complete whole space, means whole space we will take, and we can find the complete electrostatic energy. So let's take an example. So means then this formula will reduce to this form. W will be epsilon by 2 E square d tau, V is all space. Now the volume integral is in all space, so this term will be removed. So this will be your easy formula. Now let's discuss some examples based on them. First we will take for the discrete charges. So for the discrete charge, let's say we have these 4 charges, minus q, q, q and minus q. So this charge, we take this charge first, then we take this 2 charge second, and then we assemble this 3rd charge, and then in the last we assemble this 4th charge. So first, to assemble this first charge, we don't have the other 3 charges, so the work done to bring this charge will be 0 because there is no charge. Now to bring this second charge, we have to find a potential at this point. It will be due to this only. So minus q by 4 pi epsilon naught a, this will be a potential at this point, multiplied by charge will give you electrostatic energy at this point. Now to bring this 3 charge, we need to find a potential at this point due to these 2 charges. So it will be first because of this and because of this, so it will be Vn plus V2 minus q by 4 pi epsilon naught minus q by root 2a plus q by a. This is the potential, and multiply with this charge will give you electrostatic energy for W3. Now to bring this 4th charge, we need to find the potential due to all these 3 charges. It will be minus q by 4 pi epsilon naught a, then q by 4 pi epsilon naught root 2a, this distance, and because of this minus q by 4 pi epsilon naught a. So this will be your W4. Now total electrostatic energy to make this assemble the system will be W1 plus W2 plus W3 plus W4. So you can calculate that, you will get your answer. Now let's take an example for the continuous charge, means for this one. How can we use that formula? So let's see, we have a spherical cell. Now this is spherical cell, this is hollow inside, and we need to find that if charge is uniformly distributed on its surface, so we need to find that how much electrostatic energy this contains, this system. So what we need to do, we need to find the volume integral in the complete space. So we have this formula, we need only electric field, and we need to integrate for all space. So here we will take electric field, we know what is inside and what is outside, so we'll integrate from 0 to r and r to infinity, that will be for whole space. So 0 to r E1 square, and this is your volume element 4 pi r square dr, and r to infinity E2 square 4 pi r square dr. So we are using this formula only. Now see, inside the spherical cell, electric field will be 0 because there is no charge, so this E1 will be 0, only this term will be remaining, and E2 outside, the electric field will be q by 4 pi epsilon naught r square. We already calculated this value, so just put it here and take the square, integrate r with dr. This is an easy calculation for the limits. You will get, this is your answer, q square by 8 pi epsilon naught r. So this is the amount of work done or the electrostatic energy required to assemble, means to make this spherical cell which is uniformly charged with q charge. So this is the amount of energy will be there. Now let's say we have a dielectric sphere. Now this time there is uniformly distributed in the whole sphere. This is a dielectric sphere, and now charge is inside also. So now what will be the electrostatic energy for this system? So now we have E1 also, in this we don't have any E1, but now we have E1, so we'll integrate for 0 to R and R to infinity, and E1 will be, we already know this formula for the E1, we already calculated for the dielectric sphere. Electric field will be QR divided by 4 pi epsilon naught R cube, and in place of E1 we will write this, and E2 will remain same, R to infinite charge will be remain same. So the result from this one will be this, and from this one you can calculate. In the last you will just add this to that. The result will be 3q square divided by 20 pi epsilon naught R. So you can do this calculation, that's why I'm not doing, because you know how to integrate. So you know this electric field, just put it here and integrate, get the value and add it to with this. So that's how you can do that. Now let's take one more example. This time it is concentric spherical cell. Now you have two spherical cells, means there is nothing inside, nothing outside. There are two concentric cells like this. Like this you have two cells, and you have q charge on this cell and minus q charge on this outer side cell, and you need to find the total electrostatic energy for this kind of system. So we need to integrate in the whole space, so 0 to a to b, and b to infinity. So that's how we are going for the whole space. So 0 to a, electric field is 0, so the E1 term will be 0, and for the b to infinity, E3 will be 0, because this is in the if you use the Gauss law, then inside this complete sphere the total charge will be 0, that's why E3 is 0. Now the electric field will be inside only this space, and this will be only due to this charge. Using Gauss law, we can see in this sphere only this q charge will be inside, so q by 4 pi r square will be your E2. So use this and take this limit, means for the E1 will be 0, E3 will be 0, E2 will be this, and this is your volume element 4 pi square dr. You need to integrate a to b, and this will be your electrostatic potential or electrostatic energy for this concentric spherical cells. So that's how you can use this formula, and you will get your electrostatic energy very easily. So I hope you understand the today's lecture. So thank you everyone, we'll meet you in the next lecture.